Hi everyone, my name is Anthony, and today we'll be going over minimum spanning tree and Prim's algorithm. So what is the minimum spanning tree problem? We're given an edge-weighted undirected graph, G, defined by a set of vertices and a set of edges, and the objective is to find a subgraph T, defined by the same set of vertices and a subset of the edges E prime, such that two properties are satisfied. 1. All the vertices are pairwise connected, and 2. The sum of all edge weights in T is minimal, and I'll talk about what these two properties mean later. There are two types of MST algorithms. The main algorithms for finding MSTs are Prim's algorithm and Kruskal's algorithm. Both are greedy approaches for finding MSTs on edge-weighted, connected, and undirected graphs. The difference between the two is that Prim grows a tree from a single vertex, and Kruskal grows a forest of trees and merges them into a single tree. Today we'll go over Prim's algorithm. There are three steps. First, we want to initialize an MST with a randomly chosen vertex. Second, we want to find all the edges that connect the tree to this new vertex. Then we want to take the minimum and add it to the tree. Finally, we'll repeat step 2 until we've created a valid MST. So now we'll run through an example of Prim's algorithm. We first want to start with a weighted undirected graph as shown. Our first step is to choose a random vertex, and then we want to choose the shortest edge from this vertex and add it. So the two options are an edge with weight 4 and an edge with weight 2, so we'll select the edge with weight 2. We continue this process, and if there are multiple to choose from, we select one at random. So since both the edges that we're choosing from have edge weight 3, we'll select one at random and continue building our MST. Now we'll repeat the previous steps until we have a valid MST. So let's review what the properties of an MST are. There's two properties that need to be satisfied. First, all vertices are pairwise connected. What does this mean? It means that if we take two vertices, let's say this one right here and this one over here, there'll always be a path connecting the two. So there's a path connecting these two vertices as shown in red. And this applies to all other pairs of vertices. The second property is that the sum of the edge weights is minimal, meaning that if we had selected any other subgraph, the sum of the edge weights will be greater than or equal to the sum of the edge weights in this current graph. So now we'll talk about some of the data structures required to implement Prim's algorithm. We will want to have three vectors, and each vector stores some metadata about the vertices. And for each vertex v, we want to record three pieces of information. First, we want to record whether vertex v has been visited, denoted by k sub v, and this is initially false for all the vertices. Second, we want to record what is the minimal edge weight to vertex v, denoted by d sub v, and this is initially infinity for all vertices except the root vertex, which has edge weight 0. Lastly, we want to keep track of the vertex that precedes the current vertex, p sub v, and this value is initially unknown for all the vertices. So let's take a look at the pseudocode for prims. We'll want to repeat all these steps until all the vertices have been visited. The first step is that we'll want to select from a set of vertices that haven't been visited yet, and select a vertex v with the smallest current distance, d sub v. Then we'll want to set the visited flag for this vertex to be true. And for each vertex w adjacent to vertex v that have not yet been visited, we'll want to test whether the minimum distance d sub v is greater than the distance between v and w. If so, we'll want to set the minimum distance to distance v sub v and also the preceding vertex to w as v. And so now we'll talk about the complexity of Prim's algorithm. If we had used a two-loop implementation, the complexity would be on the order of v squared, where v is the number of vertices. We can optimize this by using heaps to make the time complexity on the order of e log v, where e is the number of edges and v is the number of vertices. To arrive at this big O, we'll want to break down the pseudocode into two parts. First is selecting the smallest element from the min priority queue, which is an O log v operation, and we need to repeat this v times until all the vertices have been visited, and so we arrive at in big O of v log v. Second, we want to go through all the adjacent vertices in the graph, which is executed 2e times, and updating the heap value is also an O log v operation. And so from that we can arrive at a time complexity of e log v. And summing the two together, we'll arrive at an overall time complexity of e log v. And to recap what we learned in this discussion, we first talked about that minimum spanning subtree problem. Second, we went over Prim's algorithm, an example of how Prim's algorithm works. Lastly, we went through some pseudocode and implementation details for Prim's algorithm. Thank you for listening, and in next week's discussion, we'll talk about Kruskal's algorithm.